Welcome back to Math 104. We've been discussing writing outcomes of an experiment as words of a certain length with letters drawn from a certain alphabet. If we can figure out how many different words we can write, that will tell us how many different possible outcomes there are for the experiment. That's important because we need to know how many different possible outcomes there are for the experiment in order to compute probabilities. This brings us to the very important multiplication principle of counting. I've split it up into a part 1 and a part 2 to help make it clearer. Here's part 1. In an experiment in which each outcome is the result of a two-stage process, so that for each way of carrying out stage 1, there are a certain number of ways to carry out stage 2, the total number of outcomes equals the number of ways to carry out stage 1 times the number of ways to carry out stage 2. Times rather than plus. To understand why we're multiplying rather than adding, let's look at some examples. Roll a six-sided die, then flip a coin. That's our experiment. How many possible outcomes does this experiment have? The multiplication principle of counting says there's a slot for stage 1 with 6 possibilities in it, and there's a slot for stage 2 with 2 possibilities in it because we're flipping a coin. We multiply these to find that there are 12 different ways this experiment can turn out. There are 12 different possible outcomes. Why multiplication rather than addition? To understand this, it's very useful to draw a tree diagram. There's a 6-way branching at the first stage when we roll the six-sided die, and then for each possible result of stage 1, there are 2 possible results of stage 2. That's a key phrase, for each. The total number of outcomes equals the total number of ways to travel from this point at the top of the tree all the way down through its various branches. So each branch represents a different outcome. 1 followed by tails, 1 followed by heads, 2 followed by tails, 2 followed by heads. These are all distinct outcomes. How many are there? Well, there are 2 outcomes here, plus another 2, plus another 2, plus another 2, plus another 2, plus another 2. Think of it this way. There are 2 plus 2 plus 2 plus 2 plus 2 plus 2 equals 12 outcomes. There are 6 copies of 2. There are 6 times 2 outcomes. The second stage of the experiment is giving us a bunch of 2's to add up. How many 2's are we adding up to find the total number of outcomes? Well, 6 is how many times we're adding up to. Notice also that 6 plus 2 would simply have given us the wrong number. Here's another example. From a group of 10 club members, randomly select one to be president and a different one to be vice president. How many possible outcomes does this experiment have? This too is essentially a job for stage 1 and stage 2. You're first selecting a president, and then you're selecting a vice president from among the remaining club members. There are 10 people who could be president, but once you've picked the president in stage 1, there are 9 people left who are eligible to be vice president. But wait a minute, where did it say anything in this question about stage 1 and stage 2? Where did it say anything in this question about the president being selected first and the vice president subsequently? Very good question. But we can still use this technique. We can still think of it in terms of stage 1 and stage 2. Why? In the previous question, remember the thinking. For each number that appears on the die, there were 2 possible coin results that went with it. Here too, there are 10 people who could serve as president, and for each one, there are 9 eligible people who could be vice president. The key phrase is for each. If we wanted to, we could draw a tree diagram. Every club member is a candidate to be president, and having written out all the names of the potential presidents, there are now 1, 2, 3, 4, 5, 6, 7, 8, 9 people who could be vice president with that president. Every one of these 10 nodes will have a 9-fold branching for who can be that person's vice president. So there will be 9 plus 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 9. 10 copies of 9 will be added up. When you count up the total number of pairs of a president with a vice president. Our conclusion? By the multiplication principle, there are 90 different possible outcomes for this experiment. This brings us to part 2 of the multiplication principle of counting. It applies to any number of stages, and essentially says that for the same reason that the multiplication made sense for 2-stage processes, it also makes sense for any number of stages. We are assuming again that our key phrase always applies. For each way of carrying out stage 1, there are a certain number of ways of carrying out stage 2. And for each way of carrying out the first 2 stages together, there are a certain number of ways of carrying out stage 3, etc. If we really wanted to, we could draw tree diagrams with n layers of branching, however large n is. That becomes impractical to draw, but in principle we could do it. Let's apply the multiplication principle in its full glory. How many outcomes are there in each of the following experiments? Select a family with 6 children at random, and observe the birth order of boys and girls. This is an experiment with how many stages? Think about it. 1, 2, 3, 4, 5, 6 stages. And there are 2 possibilities at each stage. So there are 2 to the 6th, which happens to equal 64 different possible outcomes for this experiment. What if we go from 6 children to 20 children? We don't need to write out all the slots. We see what role 2 plays in this problem, and we see what role the 6 played in the previous problem. The number of children, that is the number of slots, is counting how many 2's are being multiplied together. So that goes into the exponent. The answer here is going to be 2 to the 20th, which is a little bit more than 1,000,000. Here's the really important point. Once we know how to count the total number of words that are so many letters long in an alphabet with only 2 available letters in it, then we've done the computation once and for all and can apply it to all our different contexts. If this question had been about coin flipping, or about the stock market going up and down, or about true-false tests, every one of those experiments, if there are 6 stages to it, will have 64 different possible outcomes. The computation will be the same for all of those variations on the same theme of words in an alphabet with only 2 letters. The conclusion is, in any experiment in which the outcomes are represented as words of length n in a 2-letter alphabet, the number of different possible outcomes equals 2 to the n. What about when there are more than 2 letters in the alphabet? On a multiple choice test with 5 possible answers for each question, and 20 questions on the exam, how many possible ways are there to fill out your answers? There are 20 questions on the exam, hence 20 slots. So we'll indicate that there are 20 slots here, and each one has 5 possibilities in it. So 5 ways to fill out question 1, times 5 ways to fill out question 2, times 5 ways to answer question 3, etc. Ultimately, this is going to equal 5 to the 20, which is a very large number. It's almost 100 trillion. But this too is the multiplication principle at work. Another example, consider the experiment of rolling a fair die 6 times. Think of this as 6 people each rolling 1 die. You'll see in a little while why I want to think of it as 6 different people each rolling 1 die. Our first question is, how many different possible outcomes are there? You've got person number 1, person number 2, person number 3, similarly persons 4, 5, and 6. Each person is rolling a 6-sided die, so each stage of the process, if you want to think of it as stages, can be carried out in 6 ways. Again, this is a job for the multiplication principle. There are 6 to the 6th different ways that this experiment can turn out. That turns out to equal 46,656. When we work with the multiplication principle, we very quickly run into large numbers, larger than our intuition might suggest. We continue thinking about the same experiment where 6 people are each rolling 1 fair 6-sided die. Before going on to the next video, answer the following questions about this experiment. What is the probability that each person obtains a different number? And what is the probability that there is a match? That is, that somewhere among these 6 people, you can find at least 2 of them who rolled the same number. Here's a hint. Think about how these 2 events are related to one another. That's the key.